Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm lucky that I had already speakers before introducing augmented reality as Steve, so that's really perfect. And also talking about content creation a lot, like why it is actually difficult and why we are interested in this. One thing that I want to add at this point is probably mobile as well. And we think that for us, mobiles are a great platform to now do augmented reality. They provide technically a very round package that has everything that we could dream of basically nowadays. But also they're probably the one computer-human user interface that is now used most widely by the world and probably forever in the future in some sense. So we are really interested in what we can do on this kind of platform and what we can do in terms of augmented reality user interfaces. And so we are not necessarily focusing on a specific technical problem, but on all of that surrounding this platform and how to realize that. And some work we're doing on the one hand side is more technical oriented, like 3D vision-based tracking, and this is running a kind of 3D model-based tracker on a smartphone directly filmed off. And you see a bit of augmentation in there, which tries to indicate how well it's tracking and how stable it is, and how the performance of it is. Other areas are visualization. So this was a topic that Steve also mentioned yesterday. How do we present information in augmented reality? And here we are trying to, for example, show you the structure of a machine or of an object or something like this. And one way of doing this in illustrative visualization is explosion diagrams. So we could take the real object and explode it in some form. And then you get into another problem when you have a lot of bits in your view, then this might be cluttered and very complex and you can't see the individual parts anymore. So you need to organize that view as well a bit. So how do you do that automatically, and how do you react to changes in the viewpoint and in the scene and things like this? And finally, it also goes down to actually user interfaces. So this is an example where we try to use all this technology to provide a navigation user interface for a pedestrian in an indoor scenario. So we don't really have GPS or something like this. It might be much more difficult to actually establish our position at this point. And so we are using things like tracking of known targets, step counters from the accelerometer data, and so to provide an integrated experience and look at how do you need to use that, or can you integrate that to give a user interface at that point. And so we have, at some points, we have fixed locations where you get an overview map and you select where you want to go, and then you get an instruction set with individual steps and turns, and these are then matched again in the step counting against that to forward the user interface and give you a kind of a turn-by-turn navigation in a building. And this might sound a trivial use case, but Sven yesterday showed examples of our buildings, these gray boxes, and they all look the same, and it takes you 2 weeks to be there to find your room again if you start. So for us, it's a real problem. The topic for today that I'm interested in is creating content and models for augmented reality. And we need content, of course, as the information that we want to present, which is very application specific, but we also need a lot of information about the environment to be able to implement actually our augmented reality applications. We often need models for visual tracking. We need them for rendering to be able to have correct occlusions, to have lighting situations. We also need them for interaction. We often need to know that if I'm pointing at something in the scene, what is that object that I'm hitting there, how far it is away, how does the normal look there, and so on. And we want to extend this, of course, and particularly use it on mobile platforms. So we often have not prepared environments. We don't have a virtual reality lab set up or similar things. In general, the motivation for us in this kind of work is this idea of an AR browser as an ultimate location-based app. Everywhere we are, we can look at information, we can retrieve location-based information, and it should be possible to register this not only based on a GPS position or something like that, but really attach it to an object, attach it graphically as well to an object. And if we look at kind of what we can do, there was the typical idea of, originally described, for example, in the World Board paper, that you have a global reference system, you put things at a location, and this is how it works nowadays with browsers, applications that you can get already and install. They literally use a database of GPS reference information and then show this to you with all the advantages that you have a global coordinate system, which is easy then to use and to define, but also disadvantages. It depends a lot on this one sensor. You have this very indirect registration problem of putting your content into a certain location. The other ways of actually putting models, creating models, and so on, this is again this problem of really 3D modeling, which is very complex. We've heard Jan mention this before as well. It's really worth to look at how can non-expert users, end users, customers really add to that in a simple way in some form. And we are also motivated by this idea by making it so simple that we can kind of generate maybe a kind of user-generated content-driven environment for this kind of information as well. So extending this from taking snapshots, which is directly supported by the device and is a very simple operation, to also more information that is particularly registered in the environment. So this is kind of like just a concept again that I mentioned before, that with AR, this registration is a big issue, and it basically means that we need to capture when somebody creates a piece of information and wants to put it at a certain location, we need to capture something about the environment often to be able to actually make this link happen again. So we need to capture often scene environment as well as what the user actually intended to put there and how to put this there. And we think that this, particularly the scene capture, is something that the system should basically do on the fly and automatically without your intervention. It should not be something that requires the user explicitly to go out and do certain, take a lot of things. And this is also, of course, this connects back to a lot of work in vision in the last years, particularly online reconstruction and SLAM and so on, which provides us a lot of the technical input into this problem. We get something of an idea about the system, about the environment. We get some idea about what's happening with our device, how it is moving, what the user is kind of doing in this indirect way. But we don't get a lot of semantic information yet. It's all about a simple representation of geometry. Let's put it like that. So we don't have structure of the environment. We don't have it segmented into the individual pieces. We don't know how they behave together, how they operate together, as we have heard yesterday in talks where there's really a problem of analyzing this, and then this is its own task, and this is for modeled objects already, and here we're talking really about the free scene here. So on the other hand, 3D modeling, as we heard as well, and as I said before, it's also difficult, and we don't want to. We have this now on the mobile device, and the screens will not get that much bigger or something like this, so we can't really put even all this complex functionality on there in that sense. So what we are looking at is trying to build around this concept of capturing the scene somehow automatically, but then having the user add to it or use it in a simple way to create something like that. And we want to have kind of with this stable content registration and simple ways to do that, and then slowly extend this to more and more complex environments and complex interactions and scenarios. And so working on a mobile, we wanted to have something like PTEM in a very robust way that works outdoors in a lot of environment. And the first approach here was to just have a kind of online panoramic tracking mapping approach, which basically means that we create a panorama as a user pans around, which is a typical kind of behavior when you're standing somewhere and when you're using one of these applications. And we can do this in a very efficient way on the phone, which allows us to really do this even on the phone in a very real-time operation. And this was worked by Daniel here, who is also present. One of the key concepts is that we are not actually trying to have some global estimation, for example, between individual images or so, but we are just incrementally accumulating the whole information in a big panorama, and we do this on this tile-based base organization, which allows us to only look at new information when it kind of touches a tile that is not yet filled. And filled tiles in this panorama are basically just not looked at anymore. But these filled tiles are kind of put into the next step of whatever you need to do. For example, first of all, to provide some tracking, we need some kind of referencing between the live camera frame and the panorama. So whenever one of these tiles is filled, then actually we run on this feature detection to get interest points and then use those interest points again in the tracking of the panorama. So we kind of have this, we avoid all the redundancy of processing the whole image all the time. We just process it as we build it up, and that works accurate enough in this closed parameter space that we can basically do this well. And of course, it creates a system then that is very cheap to operate. To make it robust as well, there are some additional steps that allow us to relocalize matching against other data quickly in this way. And well, the basic output is a panorama, but this was not really the main focus here. Panoramas from higher resolution images taken with proper stitching and blending and so on provide higher quality here. But we also get this interactive orientation of the camera, which is the second important information for us. So, yeah, this is just, again, coming back to this principle that is basically just taken from the PTEM approach, of course, that when we split this up, we have these two modes of operation, and we can attach more and more operation to this second part here as well. A simple way is just to use these panoramas as a canvas on which you actually put your annotation. This kind of canvas allows you to have much more accurate registration than if you just have GPS positions or something similar approach to reference this. And so we have a kind of simple browsing annotation application where, based on your current location, there's a database of available annotations. And then when you move into the AR view, you actually recreate the panoramas on the fly again while you're tracking. And we are now using this panorama to actually have fast, or let's say high performance matching within that created panorama. So in the panorama, we are then able to look for any of these reference points where we have stored some visual information and are just able to detect them in the panorama. And because the panorama is built up, we just need to do this again once. We don't need to do this per frame, so we can save a lot of computational performance there. We can also add, of course, annotation, and this will basically trigger storing some more information. So the principle behind this is, again, that all we really are doing here is, for one of these locations in the current setup, when you record this, we take a patch, we store it with the annotation, and then we just search in the current environment that you're building for that patch again, and that's where we apply the panorama in the end. And because we are building up the panorama again in this step-by-step way, we just need to do this per tile. We don't need to do this on the whole video image all the time. So this gives us a very good amortization of our work over the video frames as they're coming in. There is more to it. You can, of course, use multiple of these references to estimate your orientation better or to be robust against individual outliers and similar things. But this is kind of, again, a simple principle how we can make these things work on a rather limited platform. We also extended this to get a bit of depth in our environment by using the same input again basically in a structure for motion reconstruction pipeline. Again, with the idea that we want to kind of limit the work a bit for the user here. We wanted to make it simpler. Instead of taking a lot of images to cover a certain area, we're just basically having 3-4 locations where we capture this wide angle, 2 very wide panorama images, and then run basically a basic reconstruction pipeline again. There's a trade-off in there, of course, in that we don't capture so much redundant information between different viewpoints. We are kind of limited here to less viewpoints, but we can kind of get it to work and have reasonable reconstructions. So these are kind of the principle, again, behind it. You just go to 3 or 4 locations and you capture these from the different areas where you want to be. And then you really just have a standard structure for motion pipeline where feature extraction is happening on each of these panoramas, matching, then pose recovery, bundle adjustment, and so on. And we kind of get a mesh out of this. There's some more to this, that this mesh is actually treated in a kind of volumetric fashion and then carved away to get some of the visibility more correct. And these are kind of simple results that show you that the quality is not that great, but on the other hand, we are able to do this in basically capturing the panoramas and then 5 seconds per panorama on the whole device, which is mostly matching and some of the reconstruction. Here's a bit of a bigger scene. And all of this you get from basically here 3 to up to 7 panoramas. So this is kind of trying to limit the work and give you immediate feedback for that. And having then this 3D structure in the background is basically having the panorama plus more depth information there, which we can use to put our annotations actually in 3D to locate it with distance and normal information to orient them on the surface, to use that in rendering effects and similar aspects here as well. So the last way of using this kind of method to add more content is trying to reuse other content. And here we looked at videos specifically. So in YouTube, you will have lots of people shooting videos, for example, of their skateboard tricks or other things that are happening in location. And we thought, well, can we take that kind of input and that kind of content that somebody provided and allow them to, well, register it, but rather just directly view it in that scene, in that environment, without them having to do anything else, really. And so the idea is you go to the more or less same location there as well, and you want to see that action in that video again, because you want to see your friend how they did it, and you don't want to kind of reference it back and forth between the video screen. You want to kind of see it over the obstacle life and all of these things. Well, the principle is, again, probably not novel in that sense. We need to identify somehow the object of interest here, which is kind of indicated at the beginning, and then with grab cut, we extract it and transfer it from frame to frame to get like a segmentation in the videos. And by doing that, we get, on the one hand side, the segmentation of the object of interest here, but we also get a mask for the background. And using that mask again on the video, we can establish now a background panorama, just as before, as a kind of reference here, because we have a clean background now where this object has vanished and it's not present anymore. Using that background panorama, we basically have now the information of this is the background and this is how the object moved through the whole panorama. It's not like where it is in every frame, because we know where every frame was in that panorama. We can actually like have this object move through that again. And finally, we have to, in the end, match this offline panorama to our current panorama, and that's it. We have this registration once, and after that, we actually are able to transfer basically the skater or this object in the view as it is here to the current view that you're having. And this is kind of independent of where you're looking at the moment. It's all then correctly updated accordingly. This is still work in process, so this is just a bit of a dark video here, but this is the figure as before, and it's registered here and looping again and again. So you basically get it overlaid over the live view in this live direct manner. Okay. Yeah, with that, I was maybe too quick. Really coming to the conclusion for us. This kind of scene capture gave us a lot of robustness and amortization, so that we could actually bring this functionality onto a rather limited device, such as the mobiles here. What we're really interested in the future, and this is maybe a lot of where I'm actually very happy to see all the talks here and see this input here, is we want to further understand the scene a bit more, to actually use that to constrain our interaction. So we want to kind of have somebody just click at a single thing, and the system should select what that is, or at least give you hypothesis about what it is that you might have meant at that point, and then attach it directly. It could measure, for example, a window, and then align any data or graphics that you want to register it with that geometric object, with that window. We are not necessarily implying that this should be fully automatic, so that I get a full scene understanding back. We are rather interested in having the user input something, but because the user interface itself is very limited on these devices, we want to have the user the minimal input necessary to make something happening, such as basically pressing a single pixel on the screen or something like this. And then after that, the system should provide you with like what you actually want to do there, what you could do there in the end, and how you have to do this and place this in the end. Okay, with that, thank you. And these are the collaborators. Dieter Schmalstieg is really the head of the group, and Daniel Wagner is here, Clemens, Tobias, Alessandro, and Key worked on various parts. And we have a big project that deals with particularly these handheld augmented reality parts that is also funded by Qualcomm. So we have a lot of collaboration with them as well. Okay.
Great, let's thank our speakers.